Okay, so this is the last lecture in the series of lectures which are meant to be an introduction to the course. So in this lecture, I mainly want to talk about surfaces and their classification. So in these first few lectures, I wanted to give you some flavor of what topology is about and what sort of questions we're going to be asking in the course. So I want to just say here sort of clearly one description of what topology is about, now that we have some definitions and examples at our disposal. So topology is the study of topological spaces. So we know what those are now. And their invariants. Like the Euler number. Okay, so this theme will hopefully become clearer throughout this lecture. Okay, so let me start with the definition. So a surface is a topological space with two properties. So first of all, for every point, so let me call this space S. For every X and S, there exists an open set U containing X and a topological equivalence between U and R squared. So this is saying near every point, around every point, it looks like R2. So it locally looks like R2. And then the second condition is that S is Hausdorff, which is a term that came up last time. So remember, this means for X and Y in S, there exist open sets containing these 2 points, which are disjoint. So this second condition is a technical one, but it's a reasonable condition, and we want to assume this, and I'll give you an example to explain why. So Hausdorff is a technical condition, but a reasonable one, which I'll illustrate with an example. Let me do this example on the next page. So this example is what maybe is called the plane with two origins. So let's define X as a set. It's going to be R2, the plane, together with one extra point, which I'll call P. And we're going to put a topology on the set as follows. So I'm going to tell you which sets are open. So the open sets are, so first of all, open subsets of R squared. So these are the open sets not containing P. And then sets of the form U is P together with V minus 0, where V is in R2 is an open set containing 0. Okay, so this is called the plane with two origins. So some observations or properties of X. So first of all, X satisfies condition 1. This is maybe not the most obvious thing, but let me say something about that in a second. Well, it's obvious almost everywhere except for at the point P. But X is not Hausdorff because any two open, well, so let me say it this way. If U1 contains the origin and U2 contains P, and these are open, then U1 and U2 necessarily intersect. Okay, so you can't separate the origin and P with open sets, which is why this is called the plane with two origins. So here's a picture for some intuition, but one dimension down. So this is R, and then, well, you have these 2 points, which one I guess I'm calling 0 and the other I'm calling P. And the neighborhoods of these 2 points look like, well, a neighborhood of 0 is like this. And a neighborhood of, the neighborhoods of P look like this. And there's just no way to, there's just no disjoint. Any two, any neighborhood of 0 and a neighborhood of P are going to intersect. But topologically, and this is maybe not so obvious, a neighborhood of, well, okay, yeah. Okay, this is kind of a weird example. I'm happy to talk to you about it more, but let me not dwell on it too much here. So this Hausdorff condition is necessary because this space X, this plane with two origins, it satisfies condition 1, but not condition 2, and it's somewhat pathological. We don't want to consider this to be a surface. Okay. So let me give you some examples. And some non-examples of surfaces. So first of all, R2 is a surface. This is basically immediate from the definition. R2 is Hausdorff, and well, any point you could take just U to be all of R2 is a surface. So in addition, so is R2 minus any finite set. So that's not quite as obvious, but not so hard. R, so a non-example, R is not a surface. And this is because, well, an interval say AB in R, which is homeomorphic to R, or topologically equivalent to R itself, is not topologically equivalent to R squared. So R is not topologically equivalent to R squared. So yeah, R is not locally. So R, the real line fails condition 1. So this fact requires some argument, which we'll explain later in this lecture. Actually, I'll say something about that. Another example, or actually non-example, the annulus S1 cross the interval. This is not a surface because it has these boundary components. So if you take X a point here, a neighborhood of X, well, it looks like a half plane, which is not homeomorphic to R2. Okay, but it is a so-called surface with boundary, which we'll discuss at some point. Okay. Another example, which is related to, well, polyhedra. A polyhedron is a surface. So let's see why this is true. So let's check this first condition, that around every point there's an open set topologically equivalent to R2. So let's call the polyhedron P. And let's fix a point X and P and consider cases as follows. So either X is in the interior of a face, X is in the interior of an edge, or X is a vertex. So in each of these cases, we want to say that X has a neighborhood that's topologically equivalent to R2. Well, so if X is in the interior of a face, the picture is like this. So we have X, and well, the interior of a face is topologically equivalent to R2. So I mean, we can find a small neighborhood here, and that's fine. Sorry, let me not cover up the label X. Sorry, I want to make these pictures so that you can read them and understand them if you're just looking at the notes. So let's say that's X. Yeah, so let me just redraw this, sorry. Okay, hopefully that's a little better. In the case that X is on the interior of an edge, the picture is like this. So here's some polygon and there's some other polygon. So by definition of a polyhedron, each edge is in exactly 2 polygons. And so the picture around X looks like this. And again, you can find a little neighborhood, which is topologically equivalent to R2. And in the final case, when X is a vertex, well, by assumption, in the polyhedron, we have a bunch of polygons which fit together in this way. So the definition of polyhedron, we ask for this local picture around a vertex with polygons glued around in a cycle. And that ensures exactly that a neighborhood of, in a small neighborhood around this vertex, we get an open set that's topologically R2. Okay, so this maybe provides some context for why we gave this particular definition of a polyhedron. We want a polyhedron to be locally like R2 so that it's a surface. Okay, so now I want to tell you about some more surfaces, and in particular, some surface constructions. So this goes by the name of surgery for reasons that hopefully will become clear. So here's a way to construct a surface starting with the two sphere. So you take S2, and remove two disks, like so. So you remove the interior of these two disks and then glue in an annulus. And glue an annulus along the boundary. So the boundary of an annulus is two circles, and when we remove these two disks, then we have these two red circles, and so then we glue those together and we get a new surface. So in this case, the surface that we get, sorry, the light is, I'll be right back. So if we do this, this gives us, so this surface that is pictured here is now topologically equivalent to the torus. And we can do this operation G times, and we'll call the result mg. So it looks something like this. So I'm going to draw the sphere a little bit differently. So we remove now two G disks, and we glue in G annuli, and this is what we'll call mg. Okay, and it's a surface. The way this procedure is designed specifically to take input a surface and output another surface. And right, so it's called surgery because we're like cutting and then pasting. There's a variant of this construction, which we'll also want to use. So let me make some space. Just move this up. Here. Okay, here's something similar we can do. Let's again start with S2. And now we're just going to remove a single disk and attach to this disk a Mobius band. So remember, the Mobius band has boundary, which is a circle. And so we can glue this circle along the circle here to get a new surface. So we remove a disk from S2 and glue a Mobius band along the boundary. And as before, we can do this k times, and we'll call the result n sub k. It's a little bit harder to picture because, well, it's harder to picture how this looks after you glue in the Mobius span. Okay. Okay, so this is two ways to start with a surface and start with S2 and produce lots of surfaces by cutting and pasting. And the amazing fact is that these are all of the surfaces. These are all the surfaces. So this is, I'll state as a theorem, which we'll prove eventually, called the classification of surfaces. So there's two parts to the statement. So every compact connected, okay, so these are words we haven't defined, but they're important for the statement. But let me just give this the full statement. Every compact connected surface is topologically equivalent to one of mg or nk for g at least 0 and k at least 1. So these are all the surfaces, and moreover, no two of these, meaning these examples, are topologically equivalent. Okay, so this list contains exactly every surface once up to topological equivalence. So this is rather remarkable. I mean, classification results of this type are rather rare and special. And it's, I mean, this is an extremely complete characterization of surfaces, and it's also very simple. These have these very simple and easy to understand descriptions. So let me give you an example to illustrate the classification. So the Klein bottle K, which we described last time, is a surface. So remember, we had this description of the Klein bottle as you take the square and then you identify sides in this fashion. So from this picture, we can convince ourselves that this is a surface. So I mean, if you take a point here and it has a neighborhood equivalent to R2. If instead you take a point on an edge, so maybe you take this point here, which is the same as this point, So this has a neighborhood which looks like this. This is an open set. And if you glue these together, you get a disk, which is topologically R2. And then, well, the last type of point in this picture is the corners of the square. And if you take a point on the corner of the square, it's similar. So all of these points are identified, because like this point is equivalent to this point, which is equivalent to this point, which is then equivalent to this point. You just follow the side identifications around. But then there's an open set containing this point, which is made up of these 4 wedges. And when you do the gluing, these 4 wedges come together to give exactly this picture, which is topologically R2. Okay, so this is a little argument to explain why the Klein bottle is a surface. So then by the classification, K is equivalent to either mg or nk for some value of g or k. So, well, which is it? So the classification, the power of the classification is whenever you find a surface, it has to be on this list. And so then, well, okay, so we should figure out which thing on the list it is. So we can do this with some cut and paste argument. Similar to the discussion session, which I have to admit has not happened yet, but hopefully we do discuss this. Okay, so, well, here's what you can do. So here's the Klein bottle. And if we cut it along this diagonal, then, so I'm going to cut and then re-glue. So how do I want to do this? So I'm going to cut like this. So now this is, we have this triangle, and then I'm going to take this triangle here and just move it over. So like this. And you have to keep track of the directions of the edges. So it's like this. Okay, so I will rewrite this as like this. So we have these side identifications. And now I can think about this as being composed of 2 pieces. And each of the pieces looks like this. Well, maybe I'll draw it below. So we have this glued to here, and then this is a free edge, not glued to anything else. But this, we can rewrite. We can do a cut and paste argument here as well. So let me cut here and put a little identification. And then I'm going to re-glue. So if I do that, so now I have this triangle, and then I'm going to swing the second triangle over and flip it so that the arrows match, and then I get this picture. going the other way. And this is a Mobius band. Okay, so in this picture, we see we have two Mobius bands. And in fact, well, if you leave out a little strip here, you see that you have two Mobius bands glued along an annulus. So K is topologically equivalent to two Mobius bands glued to an annulus. So this is N2. So you take the sphere, you remove two disks, and you get an annulus, and then you glue two Mobius bands along that, and that gives you the Klein bottle. So that explains how K fits into this classification. Okay, so I want to make some remarks, some further remarks about the theorem, which are somewhat philosophical in nature, and maybe tell you a little bit about the kind of things we're going to do in the course. Oh, is that what I wanted to do? No. Duplicated the wrong page. I want to duplicate this page and move it down. Okay. So here's the theorem again. Let me just write it like this. And make a few remarks. So there's two parts of this theorem. So the first, well, so let me begin the remark. So showing two spaces are topologically equivalent is a constructive problem. So part of the theorem is you're handed some random surface like we saw with the Klein bottle, and you have to construct a topological equivalence to one of these on this given list, Mg and Nk. And proving that a given surface is topologically equivalent to another one, this is a constructive problem. You have to construct a homeomorphism. So compare with the Klein bottle above, or another example to think about is, or the proof that S2 minus a point is equivalent to R2. So there, you have to, if you want to show two spaces are topologically equivalent, you have to construct a topological equivalence between them. And like in this second example, that was stereographic projection. So it's a constructive problem. You have to construct a topological equivalence. On the other hand, showing two spaces are not topologically equivalent, this is a completely different sort of beast. And this is something that you have to do in the second part here. But this is, right, so this is showing this is an, I'm going to call it obstructive problem. And let me explain what I mean by that. Okay, so let me do that on the next page. So to illustrate that, let me tell you two theorems. One is easy and one is less easy. Neither of them is so bad. But they're both theorems about two spaces not being topologically equivalent. So the first is that R is not topologically equivalent to Z. And the second is that R is not topologically equivalent to R squared, which I mentioned earlier on in this lecture. So let me mention here that here we're giving Z the topology of a subspace, topology as a subspace of R squared. Or a subspace of R, excuse me. And well, the topology you get from this is just the discrete topology. That's not so hard to see. The discrete topology on Z. So, I mean, single element sets are open because you can find open sets of R which intersect Z in only a single point. Okay. Okay, so let's prove, let me explain the proof of one. And this will tie back into explaining how showing a statement like this is an obstructive problem. Okay, so proof of theorem one. So if X and Y are topologically equivalent, so the first observation is, okay, so let me state this as an observation. If X is topologically equivalent to Y, so in general, if you have two spaces that are topologically equivalent, then X and Y have the same cardinality. Well, and this is because a topological equivalence from X to Y is in particular a bijection. Okay, but R and Z are not the same cardinality. R is uncountable and Z is countable. Cardinality. So this implies R is not equivalent to Z. So now let's think about, okay, so this is the proof here. And let me just remark that, well, philosophically, this proof is very different from showing that two spaces are topologically equivalent. We didn't construct anything. What we did was we found some property that is preserved by spaces being topologically equivalent, and then we showed R and Z don't have the same property. Here, that being cardinality. Now let's think about how we might show theorem two. Let's get a new page. So note, first of all, that R and R squared do have the same cardinality. So the same argument is not going to work. So note, R and r squared have the same cardinality, which on the face of it makes life much more complicated. So, I mean, how to show r is not equivalent to r squared? Well, we can't do this directly. We can't check every bijection. So there exist bijections from r to r squared. This is what it means that they have the same cardinality. But the claim is that there's no bijection which is continuous and has a continuous inverse. And well, it's just impossible to check that on every bijection. So we need some other way. And so what we do instead is to find a property that these spaces don't share. So, well, really, this property is what we'll call an invariant. So, okay, so now let me give you the proof of theorem 2. Let's see if I can fit it here. Actually, I'm going to get a new page. Make space. Okay, so, well, the first observation is that if r is equivalent to r squared, then also r minus a point, the origin, is topologically equivalent to r squared minus the origin. So the reason for this is, well, if you have a topological equivalence like this, up to composition on the left or the right with translation, you can assume that 0 maps to 0. So without loss of generality, f of 0 is 0. And so f restricts to a map from r minus 0 to r squared minus 0, which is a topological equivalence because f is. Okay, so that's the first step, this observation. Now the second, there's another observation, which is as follows. So if, in general, if x is equivalent to y, then x and y have the same number of path components. Or let me say it this way, or another way to say it well, okay, so let me just say this, and then let me explain. Let me not define what a path component is, but let me explain what this means in our situation. So r minus 0 has two components. but r squared minus 0 has 1. So if I remove the origin here, there's no path from a point over on to the left to a point on the right, but there are paths. Yeah, so this has 2 pieces here, but if you remove a point from r squared, if you remove the origin from r squared, you can connect any 2 points by a path. And so, right, these 2 spaces have a different number of path components, and so this implies that r minus 0 is not equivalent to r squared minus 0, and that implies that r is not equivalent to r squared. Okay, so this is the idea of the theorem, modulo some details which it will take us some time to make rigorous. Right, but the main thing I want you to take away at this point is the philosophy of this argument, which is as follows. The philosophy is that, well, okay, so a property of a space, such as cardinality, number of components, or Euler number, that is preserved under topological equivalence. So this is called an invariant, a topological invariant. Yeah, let me put the word topological in there. So if you want to show x is not equivalent to y, find an invariant that takes different values on x and y. So such an invariant you can think of as an obstruction to x and y being topologically equivalent. So that's why I stated this way, as an obstructive problem. So a major goal in topology is to create topological invariants and use those to distinguish spaces. And in the specific context of this classification theorem, the invariant that we're going to use is the fundamental group. Okay, so hopefully this gives a little more meaning to this statement at the beginning about what topology is and where we're headed in the course. So the next plan, the next sort of part of the course is to start making a lot of the things that we discussed so far rigorous. And we're going to start with some what's considered points at topology next time. All right.